Okay, everyone, maybe we can go ahead and get started. So welcome to another colloquium here at the IAS. Today it's my pleasure to introduce Professor Mikhail Ivanov from MIT. Misha is a theoretical physicist who is very well known for his ability to work at the interface between state-of-the-art theoretical physics and data analysis, bridging these ideas with state-of-the-art data sets to resolve challenges such as the nature of dark matter, the nature of dark energy, cosmic inflation, and also a lot of work related to gravity. Misha is actually not a stranger to the IAS. During his PhD at EPFL in Switzerland, he spent a year here visiting Matthias's group. And then after a postdoc at NYU, came back to IAS as an Einstein Fellow. He started his faculty position at MIT in 2023, and then was quickly recognized for his great work with the 2024 Breakthrough Prize, the New Horizons Breakthrough Prize for his contributions to our understanding of the large-scale structure of the universe, and also to the development of new tools to extract fundamental physics from galaxy surveys. So very excited to have Misha here, very excited to hear a little bit more about this program. So join me in welcoming Misha.
Thank you very much. Thank you, Nick. I would like to extend my thanks to all the organizers of the colloquium. It's really a pleasure to be here. Today I'm going to outline this program of extracting fundamental cosmology from galaxy survey data at low and high redshifts. I'd like to start off by acknowledging the, giving the credit to the brilliant postdocs and students with whom, without who this work would be impossible. This is the outline of my talk. I'm going to start off by outlining some of the critical problems in fundamental cosmology, and also mentioning as an example of a new problem that we need to solve, the dynamical dark energy as reported by the, whose evidence, the evidence for was reported by the dark energy survey collaboration. Then I will introduce some of the tools that we can use to get more information and try to clarify the critical questions in cosmology. So in particular, I will say some words about the effective field theory of large-scale structure and how to combine it with the data analysis techniques. Then I will share some of the results from the independent reanalysis of the public data that includes the undetection of the dynamical dark energy. And then I will argue that in order to get more information and really understand what is going on in this frontier, we have to get the data from high redshift surveys, and then I will discuss some of the challenges associated with the modeling of the tracers relevant for the surveys. And in particular, I will focus on the Lyman-alpha forest, and I will introduce the effective field theory technique to describe the Lyman-alpha forest fluctuations, and will show how this technique allowed me to solve some of the long-standing problems in this field, and then open up opportunities for novel discoveries. All right. The brief introduction of cosmology. I'm sure you know very well, cosmology is a very quickly advancing branch of physics, where in the last couple of decades, thanks to both significant observational and theoretical efforts, we have established a very coherent, very clear, precise picture of our universe, at least at leading order, where it all started from inflation, which was the primordial accelerated expansion of the universe that created the seeds for structure formation. And then after inflation, our universe was expanding and cooling down up to the point that the first atoms were created. And this gave us the very first picture of our universe from the fluctuations of the cosmic microwave background temperature. And then later on, the universe continued to expand and matter collapsed and formed galaxies. And we live in one of these galaxies. And in principle, the galaxies that we can observe at high redshifts, they provide us with more pictures of the fluctuations that were created during inflation. So in some sense, CMB gave us only one picture, and the galaxies provide us with a photo album. And we also have the standard model, which is called the inflationary lambda CDM model, where basically all the pictures that we have in our disposal can be described with very few ingredients, with the usual standard model of particle physics, and on top of that, with three new physics entities, which are the inflation as a mechanism to seed the primordial fluctuations, then the cold dark matter that we need to describe the formation of structures in our universe, and then something to describe the observed accelerated expansion of the universe, which typically, well, we used to believe that it was just the cosmological constant lambda in Einstein's equations. So this picture, the standard model provide a very coherent explanation to all the pictures that we had, to all the observational data at leading order. And even this picture, despite being very nice and coherent and minimal, still it left us with many unsolved questions that I divide roughly into known unknowns and unknown unknowns. So the known unknowns, things we know we don't know. And in the lambda CDM, there are all these three new physics entities, such as inflation, called dark matter, and the cosmological constant. So we need to explain them. So even though we understand roughly what inflation should do and what is the basic mechanism to produce primordial fluctuations, we yet don't know what is the exact physical, let's say, particle physics realization of inflation. So we don't know if dark matter is really cold. We don't know if dark energy is the cosmological constant. And then there are many other associated questions, for instance, the neutrino masses. So this is something that we still need to understand within the standard model. And on top of that, we are dealing with unknown unknowns. So these are things we don't know. So these are surprises, new results that come from the data, new tensions. And well, as an example of this tension, I'm going to present this recent evidence for dynamical dark energy by DESI collaboration that is also collectively known as W0 WA. DESI this year and also last year, preliminary results, they reported some evidence at the level of 3-4 sigma for the variant equation of state of dark energy. So the DESI collaboration is a spectroscopic survey that measures the distances to galaxies by employing the baryon acoustic oscillation method. And by measuring the distance to redshift relation, we can extract the equation of state of dark energy, which is parameterized, which is basically the ratio of the pressure of dark energy divided by its density, and is parameterized with two constants, W0, which is the value of the equation of state now, and WA, which is basically the first derivative of the equation of state with respect to redshift. And the usual cosmological constant, lambda term in Einstein's equations, basically corresponds to W0 equal -1 and WA equals 0. The DESI collaboration have measured distances to high redshift galaxies and reported some evidence for these parameters being different from the predictions of the cosmological constant. So in this plot, the cosmological constant corresponds to this point here, and the DESI results for different variants of the analysis are shown here. In particular, if we just take the DESI baryon acoustic oscillations and combine them with the CMB, then we get something like a 3 sigma evidence for varying dark energy. And we can also add some additional data sets with the supernovae, and then the significance for this evidence will increase up to 4 sigma. So clearly, this is a very important result, and potentially this could revolutionize cosmology. And well, this produced some excitement, both in the mainstream media outlets and on social media. And as any groundbreaking discoveries, which potentially could be revolutionary, this requires very significant validation. So we need to check this very thoroughly. And in my talk, I will present some of the independent checks outside of collaboration that I have done with my group. Now, you might be wondering whether this dynamical dark energy corresponds to known unknowns or unknown unknowns. So in fact, it's both. And right, to really understand that, it's interesting to scrutinize the signal and try to understand its phenomenology. So one thing that is absolutely necessary to fit the data well is to undergo the so-called phantom crossing. So the equation of state parameter needs to become less than -1. So -1 corresponds to the cosmological constant. And when it becomes less than -1, physically it corresponds to a regime of superacceleration. So where we accelerate with acceleration. In the classical, usual general relativity, this was believed to be a pathological regime that corresponds to the so-called big rip singularity. So basically the situation where the universe gets torn apart at a finite time. And the fact that the inference from the data suggests that dark energy used to be phantom and then became normal, it's basically impossible in a conventional general relativity. So obviously, if the signal is true, then this would mean we would have to rethink JAR and possibly cosmology from scratch. However, I should also point out that there could be more conventional explanations to this signal. For instance, you can come up with a model of interacting fields. So if your dark energy is not a cosmological constant, but let's say a scalar field that interacts with other things in the universe, like the dark matter, in that case, you can effectively produce the phantom equation of state without actually generating any singularity. One example of this model is the dark UCD, where dark matter really talks to the dark energy represented by the axion of the dark UCD. But then you can also come up with other examples. For instance, you can introduce an extra scalar fields, extra dark degrees of freedom that couple with dark energy. And in that case, again, you can move energy back and forth between the different components and effectively produce the phantom behavior. So this is the model of the kinetic coupling of dark energy to some spectator scalar field produced by Michael Toomey from my group. And you can see indeed that you can nicely account for the phenomenology suggested by the DESI collaboration. And you can also see that these different options, this option corresponds to, let's say, known unknowns. So this option involves some extra ingredients. So this is, let's say, unknown. To be able to distinguish between them, we need to do two things. First of all, we need to get better error bars, so better measurements of this equation of state parameter as a function of redshift. And also, it's really beneficial to go to high redshifts where you can see there is a big, sometimes the models that fit the DESI data well at low redshift, they produce a large discrepancy at high redshift. So this is also the example between these two models. So let's say this model produces some runaway behavior, whereas in the case of the kinetic coupling, the equation of state eventually goes back to the cosmological constant. So we need these two ingredients, high redshift data and better error bars at low redshift. So let me use this as a motivation now for the rest of my talk for these two components. And perhaps as an additional motivation, I could mention that, in fact, it's unclear whether the W and WA is really produced by dark energy, and there are explanations to the signal that do not involve dark energy whatsoever. For instance, this apparent evidence for dark energy could be driven by attention in the context of usual parameters of the lambda CDM model, like the optical depth of ionization. So in addition, the DESI data could be explained by a small negative spatial curvature. And in these cases, basically, you don't need any modifications to the standard dark energy or dark matter sectors. And in order to be able to distinguish between these scenarios, again, it's really beneficial to go to high redshifts, where you can see that the models with the curvature predict different dependence of distances on redshifts, well, as opposed to the W0 WA model. All right. Yes. Yes.
So are you saying that the WA, W0, we really need a third axis, which is the curvature? You're saying there's strong covariance with the curvature.
Yeah, this is true. These contours all assume that omega, exactly, curvature is 0. Now, if you add this, you could even fit the data without, so if you don't include the supernova, you can fit the data perfectly well without any dark energy. Yes, this is true. So there is a big degeneracy direction if you start, going for a more flexible model for expansion of the universe at low redshift. All right. But you can see that at high redshift, the degeneracy is broken. So we should be really able to distinguish between these different predictions. All right, now let me discuss these two options, the adding extra information through the full shape of the galaxy clustering, and the second option, which is going to high redshift. All right, let me start with the full shape, effective field theory-based full shape analysis. Well, to explain this, let's really go back to the beginning, to the CMB. Let me say that the CMB has been the workhorse of cosmology for the last couple of decades. And the CMB anisotropies, they represent nearly Gaussian random fields on the sky, and we can measure their correlation. So since they're nearly Gaussian, most of the information is contained in a two-point function, the power spectrum. And this power spectrum has a complicated dependence on angle or on multiple moment in the Fourier space. Well, you can see that it's a big success of the lambda CDM model that you can fit this complicated shape with only 6 parameters, which are the abundance of dark matter, the abundance of baryons, the Hubble constants, which is basically the proxy of the age of the universe, then tau, which is the optical depth of reionization, and the 2 parameters characterizing the initial conditions, the amplitude and the slope of the power spectrum of primordial fluctuations produced by inflation. The CMB power spectrum has a very strong response to these parameters. So for instance, now I'm showing you the movie, how the power spectrum of the CMB changes when I start varying this combination of cosmological parameters that corresponds to the physical density of dark matter. And you can see that given 1% error bars on the spectrum, there is only one curve that will go through the actual data. And this is how we do these fits. And this is how we extract all these parameters that are typically measured to percent level precision or even better. So for instance, for dark matter, we know that its current contribution to the energy density is 26.8%. It's a very precise number. It has the 0.8%. And this is precisely because the error bars on the CMB are very small, basically percent level. Now, with the galaxy surveys, in principle, we could play the exact same games because the galaxy distribution at low redshift measured by DESI represents a random stochastic field. This field has a cosmological origin. So the galaxy over density, again, we can characterize its properties by computing different correlation functions, the 2-point function power spectrum, the 3-point function, confusingly called the bispectrum, etc. And since now we can measure the redshift of the galaxies, we have a 3-dimensional volume of information. So in principle, now we characterize our power spectrum by a 3-dimensional wave number. And here I'm showing you the measurements from the previous survey, the BOSS survey, and you can see that the power spectrum of galaxies is also a complicated function. It has a turnover. It has also some BEO features. It has an overall slope. And again, the power spectrum has some strong response to the cosmological parameters. So here I'm going to play the exact same game. I'm going to see how my galaxy power spectrum changes as I vary the physical density of dark matter. And you can see that the variations are very strong. And given the error bars, there will be only one curve that goes through these data points. So again, we can use the full shape of the galaxy clustering in order to measure cosmological parameters, just like the CMB. And this is precisely the idea of the full shape method. So let's analyze galaxies the exact same way as we analyze the CMB. And this seems to be a good idea because CMB and large-scale structure are highly complementary. So they probe different scales, they probe different redshifts, and also they probe different physics. In particular, with the galaxy clustering, we have a direct probe of dark matter fluctuations, which otherwise we don't get to see in the context of the CMB, because CMB is a great probe of the background density of dark matter, but is much less sensitive to dark matter fluctuations. And this is the content of the Weinberg's decoupling theorem. So there is clearly benefit in this analysis. And in addition to that, large-scale structure, as I mentioned, it provides us with a 3-dimensional volume of information, which in principle contains order of magnitude more information. So when I talk about information, it's useful to recall that in cosmology, we have a nice proxy for information, which is the number of available Fourier modes. And the entire history of cosmology could be seen as a process of collecting more and more modes. Back in the day, let's say in the 80s, the best cosmological probes were given by the galaxy survey, such as CFA, that provided us with some number of modes, about a few thousand. And then later on, we kept, observing galaxies and measuring their redshift. So in principle, the galaxy surveys, they provide us with some learning curve that we used to exploit before the year 2000. Now, around 2000, we learned about another curve, which was the CMB curve. So CMB provided us with a much faster learning curve, so we could collect modes much, much faster. And we have been exploiting this in the last 20 years. And here you can see that the amount of modes in Planck is much bigger than the amount of modes, let's say, in the best galaxy survey of the old epoch, BOSS. But however, the problem with this learning curve is that it's limited because CMB basically is only one image. So we cannot push this curve by more than a factor of few. So for instance, we cannot possibly collect order of magnitude more modes than Planck. But however, with galaxy surveys, in principle, we could still continue going. And with galaxy surveys that are currently ongoing, such as DESI and Euclid, in principle, we'll get more modes than Planck. And with the Planck surveys, such as MegaMapper, we can get orders of magnitude more modes than Planck. And in the future, with the more futuristic surveys, such as 21 centimeter, we in principle could get even more modes. And these modes can be, the number of modes can be converted into the error bars and cosmological parameters. So in particular, in the case of the survey such as Euclid, we very soon will be able to measure the Hubble constant with the per mile precision, which is order of magnitude better than the current inference based on the CMB. So this just provides you with an example of how the error bars are going to shrink. And as this happens, obviously this will provide new opportunities for discoveries. Yes, Eric.
Yeah, it's really amazing
Yeah.
to show how much information is available. If I understood correctly, it's just the information that's theoretically available. The points you've
Yeah.
labeled as DESI-II and Spec-S5 come from the observational and surface experiments. Yeah, correct.
So here, to make this plot, I really counted the linear modes. I think that one of the problems associated with the nonlinearities, right? So obviously, if you don't account for that, you can get orders of magnitude more mode even from BOSS. So here, I already accounted for that. Now, in terms of the systematics, this is not accounted yet, and I think that it's not the main limiting factor here. So for instance, with DESI and Euclid, we're roughly getting the same number of modes as expected from this chart. So the biggest really problem is nonlinearities, and this is already accounted for in this plot.
This thing is the perfect measurement of the linear.
Yes, right. All right, which takes me to my next slide. So obviously, you know, this program would be too good to be true because galaxies are very hard to analyze. They are very nonlinear. So if we look at the distribution of galaxies, let's say from a simulation, then on large scales, it does look like the CMB. We see some overdense and underdense regions that roughly represent the Gaussian random field. But as we start zooming in, we start finding more complicated structures like the sheets and filaments and clusters of galaxies, and individual galaxies obviously also very nonlinear. So this observable is conceptually in a sense different from the CMB. And the onset of nonlinearity is manifest if you try to fit the galaxy power spectrum that I showed you before with linear theory. You'll see that your fit will do a good job on large scales, so small wave numbers, and then it will start failing at smaller scales. So basically, CMB is nonlinear, and you know, we have to deal with, sorry, large scale structure is nonlinear. We have to deal somehow with this nonlinearity. You know, this picture tells you that linear theory fails, but it fails not a terrible way. It fails a little bit. Okay, so basically, the idea of the EFT that I'm going to present is to come up with linear theory plus plus to correct linear theory for this small mismatch. Because in this regime, at least on large scales with numbers less than 0.2 HR megaparsec, things are still in a quasi-linear regime. So this situation that the galaxy surveys have big theory systematic error, this was clear even 20 years ago with the first precision measurements of galaxy distributions with SDSS. And here I'm showing you the variant of the plot from my previous slide produced by Max Tegmark 20 years ago, and you can see indeed linear theory fails. So back in the day, there was no clear way to correct for nonlinearities. So basically, this had a big impact on the development of this field. So the standard approach was to instead focus on some observables that are approximately stable with respect to nonlinear effects. So one great example of this observable is the baryon acoustic oscillation. And then, you know, this way of doing things, basically we're going to discard all shape information because this was unreliable. But for many models, for many questions in cosmology, we really need the shape information. In particular, I'm going to show you that shape information makes a difference for dynamical dark energy. Let's understand now how we can extract this. Historically, there were two solutions. One was to rely on numerical simulations, which is a really great approach in the case of the matter clustering, because for the matter clustering, we do have the exact solution, which is provided numerically by an n-body simulation, and its results are valid on an unlimited range of scales. However, the problem is to put galaxies into this picture, because for galaxies, we don't have the first principle model, and historically, these simulations have always been time-consuming. Now, recently, there has been a significant assist to this from the machine learning techniques, but I think that it's fair to say that they're still, the computational cost is still too high. The alternative approach was to use perturbation theory, whose recent reincarnation is called the EFT, which is based on this idea to do linear theory plus plus to correct the failure of linear theory on large scales. Obviously, this only works on large enough scales, so it has a limited range. but then it allows us to compute the theory predictions very precisely and accurately. And also, in general, these EFT perturbative techniques, they allow us to explore the extensions of the usual standard cosmological model in a very efficient way, because we can compute new templates on a time scale of seconds. We don't need to run a simulation for every single new model. And also it provides a very natural setup to marginalize over the astrophysical uncertainties. So let me discuss this perturbation theory story. So to start off, maybe I should say, why do we expect that there would be any analytic description to galaxies at all? Because in general, you can say, and rightly so, that galaxies are extremely nonlinear. And if we look at the galaxies, from within the galaxy, right? Our galaxy is extremely nonlinear and complicated. But however, to really kind of tell you why we can still build an analytic description, let me go to a more familiar case, like a simplified case of the fluid description. So in the case of the fluids, also we're dealing with, on small scales, the dynamics of the fluids is very complicated. So we have a bunch of molecules that interact via complicated electromagnetic forces. But however, on scales much larger than the mean free path of the molecules, a simplified description appears where we can introduce coarse-grained degrees of freedom, coarse-grained fields, such as the velocity field. And we can write down the equation of motion for the velocity field, which will be our Navier-Stokes equation. And the right-hand side of the Navier-Stokes equation will contain the stress tensor with the viscosity terms. And in principle, the leading order viscosity terms, such as the shear viscosity, they will represent just the leading order terms in the Taylor series in terms of the gradients. So we have a gradient expansion on the right-hand side in the Navier-Stokes equation. And the structure of this expansion is controlled by dimensional analysis and symmetries. So in principle, we could add more viscosity terms on the right-hand side. And this will represent a convergence gradient expansion, because they will be suppressed by the ratio of the mean free path over the typical large scale we're looking at. So in the context of the fluids, typically this is the wavelength of the sound speed. So basically we have this hierarchy of scales. We have the mean free path, which is the scale of difficulty, and we have larger scales where things simplify. Given finite precision, we can always write down finite amount of terms on the right-hand side in the Navier-Stokes equation and get very precise predictions. So this is the sketch of what we're doing with galaxies as well. Because for galaxies, again, the picture is that we have extremely complicated dynamics on small scales, on the scales, let's say, smaller than the size of the dark matter halo. But however, a lot of cosmological information is actually located on the scales of the order of 100 megaparsecs, so it's much greater than the scale of difficulty. So now we are going through this route again. We start from a difficulty scale, but then on larger scales, simplified description appears that is based on the coarse-grained degrees of freedom, such as the coarse-grained velocity and density field. And the velocity field basically will satisfy the Navier-Stokes equation that will have some stress tensor. And in principle, we don't know the structure of the stress tensor. It could be, well, physically it's produced by small-scale clustering of dark matter that is responsible for the halo formation, and also is sensitive to new physics, to what exactly do we assume about the nature of dark matter. But on large scales, it doesn't matter, because we can write down the expression for the stress tensor just based on symmetries and dimensional analysis. And it's the coefficients, such as the viscosity, that will appear in this expansion that will capture different small-scale scenarios. But on large scales, otherwise, the dynamics will be completely simplified. And this is the point of the effective field theory for cosmic structure, to come up with an effective description for the dark matter and galaxy distribution, treating them as a fluid. So in this slide, I'm showing you the description of dark matter, which is kind of a backbone of the cosmic structure. Now, in the context of the galaxies, we can play the same game. So the basic difficulty with the description of the galaxies is that galaxies trace the underlying dark matter field in a complicated way. So here I'm showing you the result of the simulation, where the gray structure corresponds to the overdensities of dark matter, and the yellow blobs, they correspond to the simulated galaxies. And you can see, if you look at this picture only for 5 seconds, the only thing that your brain will remember is that roughly there is a one-to-one correspondence, right? If there is an overdensity of galaxies, also there is an underlying overdensity of dark matter. But if you look at this picture for more than 5 seconds, you will start seeing that, for instance, there are some regions in this map where we see some complicated dark matter structure, but not so many galaxies, right? So this correlation is not one-to-one. So this corner will appear as a void of galaxies, but in fact is full of dark matter. So in the EFT, again, so what we say is the following. The overdensity of galaxies is some function of the dark matter distribution. And we're going to write down a Taylor series for this function. And the coefficients in this Taylor series we're going to treat as 3 parameters. And the first non-trivial function that you could write down will be linear. And this linearity will precisely reproduce this picture that you will have in your brain if you looked at this picture only for 5 seconds, 100% correlation. So this is what this equation describes. And this correlation, in other words, is something that just follows from the symmetries. You cannot have anything else. Now, if you want to have a more fine-grained pictures, you go to smaller scales, you will start being sensitive to higher order terms in this expansion. So you'll have to write down something that is called the higher order biases, so delta squared, and also symmetries basically don't forbid having a term that corresponds to the square of the tidal field. So you must have this term as well, so-called tidal bias. And in principle, you can continue and write down more and more complicated terms in your Taylor series. And this Taylor series, even though it's very general, it's still quite restrictive. For instance, you cannot write down the gravitational potential here because this would break the equivalence principle. So symmetries and dimensional analysis, in the end, they play a very important role in this bias expansion. And all the different scenarios that correspond to different galaxy formation models, they are captured, they are encapsulated by these 3 coefficients of this Taylor series that we called bias parameters or nuisance parameters or EFT parameters. So now if we marginalize over these parameters, effectively you're just marginalizing over all possible uncertainties associated with the galaxy formation. So this is basically the point of the EFT program, to use this Taylor series and ensemble average and compute the galaxy observables in terms of the Feynman diagrams. And once you go through these expansions and Feynman diagrams, then you can produce a model for the power spectrum that at some order, so-called one-loop order, will match the data really well. And now having this model, you can fit the data on galaxy clustering and try to see, if you can constrain cosmological parameters. And this is the game that we have been playing the last 5 years or so, doing these feeds on various data sets, and we're able to measure the cosmological parameters such as the abundance of dark matter and the Hubble constant and the clustering amplitude sigma 8 with precision, which is kind of similar to the state-of-the-art CMB data sets. So this was an interesting outcome of this program. And in principle, now there are many codes that compute this one-loop predictions for you, so you don't have to go through all these steps in this computation. You can just use, for all practical reasons, these codes. Yes, Chris? Yeah. Very good. Yeah. So in principle, yes. So if you're a true kind of EFT person, yeah, for you, they in principle could take arbitrary values. They should still be, since it's a Taylor expansion, they better be like order 1 numbers, right? They could be bigger than 1, so this could be problematic. I'm going to discuss this in a second. But yes, in principle, yeah, they could be arbitrary. Now, if you have an actual model for galaxy formation, of course, they will start taking particular values. And in fact, you will see that they're extremely correlated in certain models. And there will be some correlations imposed, for instance, by the halos themselves, because the halos, they kind of fix all these parameters for you, right? But yeah, here we just marginalize them, assuming that they can be arbitrary. Yeah, exactly. Okay. Yes. Dark matter part, yes. Yes, it's also an unknown parameter, yes. It's a constant, yeah, it doesn't have, exactly. So all the spatial dependence is fixed, let's say, by the gradients here. So here the spatial dependence will be fixed by the density field, but otherwise, here, all these parameters are truly constants. Thanks. Any more questions? Yes. Yeah, very good. So the physical meaning for this effective sound speed is the following, that so you have dark matter particles, that, well, normally in the absence of, let's say, a big structure formation, they will just go through each other, but in fact, they start gravitationally interacting and they, collapse and form a halo, right? So there will be, so effectively, in other words, what happens is you have some sort of dissipation because of which your two particles don't go all the way, right? So they get trapped. So from these simple arguments, you can estimate what this parameter should be. So it really, from the large scale point of view, it acts like a, well, some, let's say, dissipative. It's like a combination of viscosity and the sound speed, in fact. Yeah, but you can estimate, and roughly you will get a scale that corresponds to, let's say, 1 megaparsec, right? Exactly from this argument that effectively it acts like dissipation. All right, any more questions? All right, if not, let me then, yeah, let me just say that these results were also noticed by the big collaborations. So in particular, DESI has adopted our EFT full shape analysis as the main analysis tool beyond the baryon acoustic oscillations, but they haven't implemented all of our tools yet. For instance, they didn't use the bispectrum, so they left a little bit of work for us to do. And recently, with my collaborators, Anton Chudak and Oliver Philcox, we reanalyzed the public DESI data on the full shape of the galaxy cluster, including the 3-point functions, the bispectrum, and we're able to measure the cosmological parameters again. And we found that the bispectrum does add some interesting extra information that allows us to restore a little bit the concordance between the CMB and the DESI. And this kind of tension that you can see, let's say, without the BO, without the bispectrum, is something that is precisely, responsible for this W and WA. I will talk about this in more detail shortly, but yeah, you can see that in principle, this program kind of keeps making a difference here. All right, yes. Good. So yeah, you can do, so here you can do two things. You can ignore the BO, ignore the cross covariance because the BO, we're using the BO from DR2, which has a bigger footprint. Then you can also calculate the covariance, for instance, analytically, or you can get some estimate from simulations, and in fact, they will tell you that this cross covariance is very small. So yeah, the rough answer is that you can just combine without cross covariance, and this is because the footprint of DR2 is bigger. Okay. All right. Then having these tools, we produced also many analyses in the extended models. So it turns out that these tools are specifically sensitive to models where dark matter has extra scales and it has some admixtures that don't cluster, same way as the cold dark matter species. So if you have this kind of model where dark matter has multiple species and one of them doesn't cluster on large scales, then this will produce an observable suppression in the galaxy power spectrum. And this will allow us to test this kind of mixed dark matter models. And this scenario is already realized in nature by massive neutrinos, because massive neutrinos in the cosmological context, they do behave like warm dark matter. And in principle, with these tools, we in the long run will be able to detect the neutrino mass using this technique. But in principle, you could also have, let's say, some genuine warm dark matter mixtures or axion dark matter, and all these additions you can test with galaxy surveys with these techniques. In addition, these tools have been specifically very sensitive to the change in the initial conditions that corresponds to the primordial non-Gaussianity and the presence of different particles during inflation. So we're able to also run some analysis, basically searching the imprints of massive particles during inflation in the correlations of the galaxies, because if these particles existed, they would produce extra correlations in the 3-point function of galaxies. So we didn't find any, but this was a nice example that shows that these tools really allow you to explore new physics scenarios that are impossible to do otherwise. And the last family of models, they have to do with the Hubble tension. Typically, the models that are designed to resolve the Hubble tension, they produce some observable modulations of the galaxy power spectrum, and you can test those as well. And we have done so, and typically the current galaxy clustering data just rules out those models. Okay. And something that I mentioned at the beginning is that now we can also just try to reanalyze the DESI data in the context of the dynamical dark energy, including the bispectrum, including this full shape stuff. And we're able to, well, actually show that if you do that, then the evidence for dynamical dark energy significantly reduces. So here you can see the usual CMB plus BU result, the 3 sigma evidence. But once you add different combinations of the full shape data set, in general, the you start overlapping with the cosmological constant point within 2 sigma. And this holds true even if you add the supernova, although the supernova really try to pull it back. So from this perspective, it seems that W0 WA could simply be a statistical fluctuation, but you can still have a 2 sigma preference for it if you add a supernova. So the situation is a little bit unclear. And again, to really make progress in these questions, we have to go to higher redshifts. So let me now outline this higher redshift survey program. So the fact that to continue making progress on the cosmological questions, we need this high redshift survey data. This was already recognized by the funding agencies. For instance, the P5 report, it encourages very strongly the transition from DESI to DESI-II, and then later on to Spec-S5. So here you can see the timeline of these different surveys. So DESI is still taking the data, but it will start doing so soonish. And then in 4 years from now, DESI-II will start operating, which is basically an extension of DESI to high redshift galaxies. Maybe here, if you look at the chart of the constraints of the dark matter density, you can see that DESI-II will really start looking at the galaxies at a redshift around 3. And then as DESI-II kind of operates and we learn more how to deal with these galaxies, we'll get more information about the relevant for the next generation of galaxy surveys, Spec-S5. So currently it was supported in the P5 report, and it's in the process of R&D, so research and decision. But in general, it was emphasized that this will be really groundbreaking for cosmology, because this will allow us to increase the number of modes quite significantly compared to DESI. So here you can see the number of modes as a function of redshift. And in DESI, well, first of all, we're still far away from the cosmic variance limit. But then there are many more modes out there at higher redshifts that DESI is not collecting at this moment, and this will be targeted with these future surveys. So having, let's say, order of magnitude more modes than what we have now will be a really game changer for the curvature of the universe, for these features in the matter power spectrum, non-Gaussianity, dark matter, and other questions. So this all looks very, very exciting. However, there are some challenges with the understanding of the high redshift galaxies. So let me now quickly discuss these different tracers. So there are 2 kinds of galaxies that will be targeted. The first ones are called the Lyman-alpha emitters. The second type of tracer is called the Lyman break galaxies. So they are identified by their characteristic spectral features. So for the LEs, there are bright emission lines. For the LBGs, there is a flux decrement towards the UV in a galaxy rest frame. So these galaxies will be the primary targets for this future surveys. And on top of that, there will be a very significant amount of the Lyman-alpha forest in the spectra of those galaxies. So we're used to the Lyman-alpha forest in the spectra of quasars. So the forest is the collection of absorption lines in the spectra of distant quasars that are produced by the neutron hydrogen clouds that are absorbing the UV light from those quasars. And typically in the context of the quasars, we have a high individual signal to noise of the forest, but we have a low number density of the targets themselves, just because in the universe there are very few quasars available for us. But however, with this future galaxy surveys, we should be able also to see the Lyman-alpha forest in the spectra of the Lyman break galaxies. And in fact, there was already a measurement of the 3-dimensional Lyman-alpha distribution from the LBGs. Well, you can see that the individual signal to noise is lower than in the case of the quasars. Well, you really need to kind of squint to see the forest in this picture compared to what we had before for quasars. But the statistics of this spectra will be really amazing. So even now we can we can see something like 1,000 LBGs per square degree, and in the future this could be increased even further. So statistically, we're going to get more information in the forest, much more information than what we have now. However, modeling these different tracers is challenging. Let me first talk about the modeling of the high redshift galaxies, specifically these LAEs and LBGs. Well, the challenges with them is that typically to model high redshifts, we need, high redshifts are characterized by large volumes. So we need to simulate large volumes, which are computationally very prohibitive. And also, since these are star-forming galaxies, we need to get some high resolution. So the parameters of the simulations are very, very demanding. So it's very hard to simulate them. And also, the physics is not very, very well calibrated. So for instance, if we take even the small simulations available now, you will see that it will be hard to match the luminosity function. So obviously we need to, tweak our simulations and inform them a little bit. Another problem that comes with the modeling of these galaxies is that maybe, some of the simplest empirical semi-analytic techniques, such as the Hall occupation distribution, they don't seem reliable for them. And in particular here, I'm showing you some of the occupation distributions of the galaxies from available simulations, MTNG and Astrid. And you can see that this, the typical probability distribution as a function of the Halo mass looks very different from the standard HUD models of Zhang et al. So there is no, for some of them, you can see some kind of a step function feature for the centrals, right? So you don't have a central until some threshold value, and then you have only one central galaxy. So this is only true for certain selections, and for other selections, the HUD functions, they look very, very different from the standard ones. So clearly some extra calibrations are needed. And to be fair, also it's unclear if the EFT is going to work for them because we're observing bright objects, our bias increases. So bias parameters, they represent coefficients in the Taylor series. If you have big coefficients, that means that the radius of convergence could be really small. So this was also a problem. And at least this one we could test. And we have done so with Jamie Sullivan and Carol Cuesta-Lazaro here. So we measured the bias parameters of galaxies from available hydrodynamical simulations. We carefully select those galaxies, matching all the available data that we have. And we found actually that EFT works quite well, despite the fact that their bias parameters are quite high. So you can see, for instance, that this B2 could be as high as, let's say, 8. But nevertheless, this, the big values of the bias parameters are compensated by the smallness of the dark matter fluctuations at high redshift. So in the end, EFT works as well as for the current galaxies, for these high redshift galaxies. And you can see that, given that other tools at the moment are unavailable, EFT could really shine in the area of this high redshift surveys in the future. So in the simulation, yeah, we used several criteria. We used the fluxes, we used the stellar masses and metallicity, trying to really match the observed, the observations that we have from small scale, from small area surveys. Okay. Right. And in the remaining few minutes, let me now talk about modeling of the other challenging tracer, which is the Lyman-alpha forest. So in the context of the Lyman-alpha forest, we see this absorption features in the spectra of different quasars, and we can build different correlations. So we can calculate the correlations of the Lyman-alpha fluctuations along the line of sight. This will give us the 1D correlations. Then we can correlate different skewers. This will allow us to extract the demographic information, so to get the 3D correlations. And then since the Lyman-alpha forest lives in a spectrum of the quasars or galaxies such as LBGs, we can also cross-correlate the forest with the source quasars or galaxies themselves. So we can get also cross-correlations. And this is just a picture, which is a little overwhelming on purpose, that shows you all the data that we have at the moment. So we have very precise measurements of the 1D power spectra from DESI. We have three-dimensional demographic Lyman-alpha forest from the previous survey EBOS, also from DESI, and we have it both in a spectra of quasars and LBGs, and we have different cross correlations between the spectra and quasars, LEs, LBGs, etc. So really we have a gigantic volume of data. And for many of these data sets, the typical error bars are the percent level. So we need theoretical tools that match these precision requirements, which is especially relevant given that Lyman-alpha forest also gives us a unique probe of physics at high redshifts and small scales. And particularly in this chart, I'm sort of mapping distances and redshifts probed by different tracers. And you can see that the low redshift galaxies that I discussed in the first part of my talk, they probe a relatively small fraction of distances and redshifts, whereas the Lyman-alpha forest can really go to higher redshifts and small scales that no other tracer can do. And thanks to these advantageous properties, the Lyman-alpha forest was providing leading constraints on neutrino masses, axions, primordial black holes, and other non-minimal cosmological models. And an example that kind of got interesting recently is provided by different models that try to resolve the Hubble tension. And typically, these models will produce a different shape of the galaxy power spectrum and the matter power spectrum that you can also check through the Lyman-alpha forest. And for a lot of these models, such as the self-interacting neutrinos, you have, let's say, percent level modification of the matter power spectrum on the galaxy scales or weak lensing scales. So you won't be able to see any anomaly in the corresponding data. But however, on the scales of the Lyman-alpha force, you can produce a gigantic effect up to 20%. So clearly, these models become testable with this data. So this is just one example that kind of shows that the Lyman-alpha force continues being one of the important tools to probe beyond standard model physics. But however, despite all this power of the Lyman-alpha forest, the field itself was in a somewhat controversial state a few years ago. So for instance, the one-dimensional, so the inference of the linear matter power spectrum from the Lyman-alpha forest was in a 5 sigma tension with the prediction based on Planck. So here you can see the result of the EBOS Lyman-alpha forest, or in a 5 sigma tension, and also this other experiment, XQ100, high resolution experiment, also was in a tension. So it was unclear what was going on in the case of the 1D correlations. Also, there were some problems with the 3D correlations. So since the very beginning of the Lyman-alpha forest 3-dimensional measurements, the BEO extracted from the 3-dimensional correlations was in tension with the predictions of the lambda CDM, and the level of this tension was varied. But there were always concerns that actually the BEO itself is not a good standard ruler in the case of the Lyman-alpha forest, because there was no formal proof that it's preserved by the Lyman-alpha physics. And in fact, there were some simulations that show that it's not a good standard ruler at all, that show that the shift of the BEO scale due to nonlinearities could be as high as 1%, which is 1 sigma statistical error of DESI at the moment. So there were all these concerns. And on the theory sides, also there were some concerning trends. So the standard way to model the 1D correlators, since they're sensitive to small physics, was to run simulations, but the simulations were expensive. So various approximation schemes were involved. And even if you could run the simulations, still there was some uncertainty due to the grid completeness and grid extrapolation and interpolations. So definitely there was some value in alternative approaches that don't rely on these approximations. And in the context of the 3D correlations, the kind of standard way to model the data was to use some fitting functions that were calibrated against simulations that were really doing a good job by fitting the data, let's say, within 10%. But as I told you before, we already now have 1% precision measurement, so we need tools that can match this precision. So obviously, the theoretical tools were not good enough. So I decided to address this problem using these EFT ideas. So again, in EFT, you only need to use symmetries and dimensional analysis. So for galaxies, we have this beautiful bias expansion that worked really well. But galaxies, so they have a bunch of symmetries, such as the equivalence principle and the Galilean symmetry. So those symmetries will have to be satisfied by the forest as well. But however, galaxies on top of that also have the 3-dimensional rotational symmetry, right? So galaxies obviously don't care about you as an observer, which is different from the Lyman-alpha forest because it's a tracer that kind of fundamentally lives on the line of sight, and the probability to form an absorption line depends on the line of sight properties. So that means that from the theory point of view, that you have less symmetries, you only have the rotations around the line of sight. So that means that your effective bias expansion should contain more terms. And at leading order, for instance, in linear theory, there should be an extra term that will look like a contraction of the velocity gradient with the line of sight. And then at higher orders, there will be more complicated terms of the similar structure. So basically, the bias expansion for Lyman-alpha forest will introduce many more nuisance parameters, but on the other hand, its power is that it's based only on symmetries. So you can still kind of in a relatively straightforward way derive all these terms here. And we have done so. So I derived all these terms and computed their predictions and then fitted them against the data. And I was able to show that this EFT technique allows you to fit the three-dimensional Lyman-alpha force correlations, the one-dimensional Lyman-alpha force correlation to better than 1% precision. And also this technique could be extended easily to cross correlations of the forest with the high redshift tracers, such as quasars, LBGs, and LEs. So altogether, this technique was working really well, which emboldened me, and I started applying this to the data. And with my group, we reanalyzed the public data on the Lyman-alpha forest from eBOS, and we're able to fit this data, the one-dimensional power spectra, and extract some of the strongest measurements of the clustering amplitude of mass fluctuations, and also the neutrino masses, which used to be the strongest before DESI. And also this EFT technique, this EFT likelihood allowed me to restore the consistency with Planck. So the EFT likelihood now, well, has a less tension with Planck, tension maybe at the level of 2 sigma. So we reduced the tension from 5 sigma to 2 sigma. And also this EFT results, they match quite well an alternative way of analyzing the data based on the other set of emulators by Simeon Bird called PRIA. So altogether, you see that we were able to restore also the consistency between theory and simulations. I mean, there is still a little bit of a tension. We're working on this, but altogether, we significantly reduced the tension. All right. In the context of the BEO, also these techniques were making a big difference. So we're able to test this story about the systematic shift more accurately. So we found indeed that the Lyman-alpha force is biased by about 0.3%. So the BEO is biased, and this 0.3% corresponds to statistical error of the full DESI survey. So this could cause a big problem. But however, the shift within the EFT can be fully forward modeled. So in fact, if you use EFT as a model to fit the BEO data, then there will be no systematic shift whatsoever. And we tested this again against simulations, and we were able to show that the BEO inference is completely unbiased to 0.1%. So this way, we're able to resolve the previous conundrums with the BEO data. And the last application that I'm going to show is that in principle, this effective bias expansion for the Lyman-alpha forest, this is the theory of everything as far as the forest is concerned. So it's not only the theory for the power spectrum of the 1D correlations, it's the theory for the entire field. So we took this and applied this at the level of the field, and we're able to see that, in fact, you can use this EFT bias expansion instead of the simulation to produce the Lyman-alpha forest maps. So basically what we have done, we took the initial conditions from a simulation and plugged this into this expansion and compared the result against the simulation. Well, we had to adjust these parameters to get a good match, but still you have only few parameters in the end compared to hundreds of thousands of pixels in the simulation, and we're able to reproduce the map of the full simulation very, very precisely. So there are still a little bit of residuals in the Lyman-alpha forest flux because EFT doesn't work on small scales, but all large-scale features were reproduced very accurately. And also you can compare these maps with the ones that we generated for the dark matter halos that are kind of proxy for the high redshift galaxies. And again, you can see a very nice correlation between them, and you can see that EFT is doing a good job at reproducing these maps as well. So why this is interesting? So this is interesting because now using these techniques, we can produce large-scale, high-quality maps for the forest and also for the clustering of galaxies. So basically, we can start from a small-scale, high-fidelity numerical simulation of the forest, calibrate the bias parameters of the EFT, and then we take the large-scale initial conditions from a big box and just apply these bias parameters and use this forward EFT model instead of the simulation. And this way we can produce maps whose properties on large scales will be completely consistent with all the symmetries of the problem. So in other words, all the large scale properties of this map will be exactly the same as the properties of the full map that you could get if you could run a big simulation in a big box. And this is guaranteed basically by the fact that the EFT is based on the symmetries. And now we can generate entire light cones. We can produce many snapshots of the Lyman-alpha forest. We can also produce snapshots for the galaxy fields, for the high fidelity simulations that really produce galaxies that otherwise cannot be described with the semi-analytic tools. So we can simulate the entire high redshift survey using these tools and produce realistic fields that you can use for all possible auto and cross correlations. And I think this opens up really many novel opportunities for analysis, such as the field level inference, or let's say the production of the mock catalogs for future surveys. So I think I'm running out of time, so maybe I'll just put my summary here, and I will stop here, and thank you for your attention.
Any questions for Misha?
Very nice talk. I wanted to understand, how do the bias parameters depend on the various parameters, cosmological parameters?
Yeah, this is an excellent question. So for galaxies, we studied this in detail with Carol. So let me see, maybe if I have an extra slide about this. Okay, very good. So for galaxies, so for instance, we studied how the bias parameters depend both on the, let's say, semi-analytic, on the halo properties that are imposed by the semi-analytic model, such as HOD, and also on the parameters that we have in the simulation. So for instance, in this plot, I'm showing you the bias parameters predicted from the semi-analytic models, the HOD in gray, and also the bias parameters measured from the Hydra simulations, ASTRS and Millennium, for different star formation cuts. You can also play with other parameters of the Hydra sim, and you can see that in general, first of all, there will be a big dependence on the cuts that you're imposing. And second of all, there will be also dependence on the simulation that you're using, right? You can take the same cuts in two different simulations and it will produce slightly different bias parameters. But the key point that we discovered is that this doesn't matter, because they will just move along some directions that are imposed by the dark matter halos, and these directions are respected even if you use the same analytic model, such as the HOD. So I feel like the answer is that, yeah, these bias parameters, their values, they depend a lot on the model you're using. They depend a lot on the properties that you're selecting, that you're choosing in your simulation to select the galaxies. But in the end, there are higher level things like the correlations between them, and those things are, the trends are very well predicted in any simulation or even in the semi-analytic models.
Thank you for a very nice talk. Can you tell what in this analysis creates the difference in the DESI results and eliminating the W0 WA effect?
Oh, absolutely. Yes. So I was showing, okay, maybe I need to go back to the slide where I was showing the movie. Okay. Somewhere here. So in this movie that I was showing, the galaxy power spectrum was a very sensitive function of the dark matter density, right? Oops. So in principle, we could measure, we can infer the dark matter density from the slope of the power spectrum, regardless of the distance information. And the DESI results, to some extent, they are driven by two things. First of all, they are driven by the fact that the inference of the omega matter from the BEO is different from that of Planck. And the second of all, because also these points are scattered a little bit, that kind of preferentially really W0 with the extra acceleration. So the fact that allows you to reduce the tension is that there is an independent measurement of omega matter from the shape that is consistent with Planck. So that reduces part of the preference. So roughly this 4 sigma preference could be split into a wrong omega matter and an extra scatter that really prefers this extra acceleration, high redshift. So the first part can be really removed if you add this. So this is the extra information that allows us to, let's say, reduce the evidence for the W and WA in this analysis.
Do you have any pressing final questions before we go to the call-in? Michael?
That's a good quick one. If you could go back to your bias expansion for the Lyman-alpha forest.
Okay.
I was wondering where peculiar velocities in the Lyman-alpha forest come into that, or how we think about how they enter. So that is this the density as observed or after correcting for peculiar velocities or what?
So if you're a true EFT person, so you say, I don't even want to ask these questions. I just write down all operators consistent with symmetries. And for instance, there have to be this operator that is consistent, and it needs to have a gradient because otherwise it will violate the Gaussian symmetry. Now you can ask more complicated question. Okay, we know, for instance, that the Lyman-alpha forest is a nonlinear transformation of the optical depth field, right? Then how do these terms appear? So these terms then will appear from the following. So the optical depth field also feels Redshift space distortions, right? Because you need to go from the tracer frame to your frame. So there will be Redshift space distortions, and typically the coefficient in front of them is fixed by the, it's the growth factor that we measure in RSD. But however, in the map by the Lyman-alpha forest, we also have, when we produce, right, so in this map, we also have, if you want to compute the mean flux and the fluctuations, there will be a dependence on the mean optical depth. So then you will have the mean optical depth multiplying the growth factor. And this is physically in the end why you have a free parameter in front of the velocity bias. But this velocity bias in the Lyman-alpha forest expansion, from the point of view of the optical depth, just corresponds to the usual kind of quasi-Redshift space distortion multiplied by the mean optical depth.
Then maybe we can thank you one more time and head over to a follow-up.